Welcome to this afternoon session in our workshop on the limits and potentials of deep learning in robotics. So we are very happy to have three more invited talks this afternoon. Walter Scheirer from the University of Notre Dame is going to open the session, and then we will hear Raya Hatzel from Google DeepMind and Ashutosh Saxena from Cornell University. After the coffee break at 3:30 to 4, we will have the poster session and then the panel discussion at the end of the day. So please welcome Walter Scheirer from University of Notre Dame.
Great, thank you. So in the first talk, a question came up about what do you do if there's unknown input coming into a recognition system? We know machine learning works really well when we're within our data sets. And pattern recognition in general has been evaluated in closed worlds. So your typical benchmark in computer vision looks something like this. Assume we have examples from all classes. This is a slide showing you some examples from the Places 2 dataset, which is part of this year's ImageNet competition. And it follows the basic paradigm that was laid out, I'd say, as early as Caltech 101 in computer vision, where you have some set of visual classes, and the goal is multi-class classification. Your training regime has all of the classes. You train on instances of these classes, hoping to assign these labels when you move on to the testing set, which has the same exact classes, just different instances of the objects, or places in this case, at hand. And this works, and this gives us some idea of how well we're doing with respect to algorithms. It lets us produce useful benchmarks. And again, the idea is very old. In fact, Caltech 101 wasn't the first set to do this, though it's probably the first very popular set that introduced this idea. You can go all the way back to the 1970s to the work of Takeo Kanade, looking at these closed worlds of faces he was interested in classifying back as early as, I think, 1972 or 1973. And the field just kind of kept doing this. You know, we want to do nice controlled testing. We need controlled evaluations and benchmarks to understand how well we're doing. And we want to see some progress, of course. But if you look at real data, and again, this is a room filled with roboticists, so images like this are more typical. Very different from the scenes I just showed you, again, in a state-of-the-art computer vision benchmark. Here, there's nothing really particularly salient in this image. It's just a picture of a street. Maybe we want to detect cars in this image, where we have an autonomous vehicle scenario, or maybe the road, et cetera. But there's a lot of other stuff here, a lot of clutter. We'd have to reject the trees, the signs, the telephone poles that appear in this image. In fact, this is rather troubling when you think of autonomous vehicles, because people may jump into the road, small children, unanticipated actions happening that our visual system has to process and either reject, accept, or make some sort of decision about. And so we call this problem open set recognition. And I'll offer you this definition. Open set recognition is incomplete knowledge of the world, present at training time, and unknown classes can be submitted to an algorithm during its operation. This is the way you and I deal with the visual world. Those multi-class closed set classification problems are fairly contrived when it comes to real-world recognition. Now, at least once per talk I give, I invoke my pal here, Don Rumsfeld, who, among other things, is remembered for the following speech that began, "There are known knowns." And Rumsfeld went on to enumerate an interesting taxonomy about things we know we don't know, and things we don't know that we don't know. Of course, he was talking about national security issues on the eve of the invasion of Iraq. But what he had to say makes a lot of sense for thinking in general. And we can relate it back to machine learning in the following way. We know we have known classes. These are the classes with distinctly labeled positive training examples, which may also serve as negative examples for other known classes. We may have known unknown classes, which could just be negative examples that are labeled as negatives, not any specific class assignment. And then we have this troubling category of unknown classes. These are these things that are unseen in training. What do we do with those? Is this a real problem for us, or should we just eschew the whole thing like we've been doing thus far, mostly in computer vision and robotics? Let's think about vision problems in order of this term openness, meaning how much unknown stuff are we going to see as inputs come into the system. As I mentioned before, multi-class classification isn't open at all. It's a closed world. For training and testing, all of the samples come from some known set of classes. We could then move to something in computer vision like face verification, where there's a claimed identity, but there's still a possibility for imposters, even though we're doing one-to-one matching. For instance, you could think of an authentication system. I sit down at my computer, I submit my face to the computer as an alternative to passwords, and unlock the system. The computer only expects me to be present there if it's my laptop, say, but anybody could sit down in front of the computer and try to authenticate, so we'd have to reject all of those unknown inputs. More familiar to the computer vision community is detection as a problem. Here, there's typically one or maybe several classes that we want to detect in a scene. That would be drawing a bounding box around the identified object of interest so we can localize it within an image. We won't make any strong assumptions about the object appearing there or where it will appear. And everything else in the world would be negative. So most computer vision people would tell you this is the canonical open set problem. Many of our data sets have a detection mode, ImageNet for instance. But when you think about this and you think about the training regimes, oftentimes we're handed a set of backgrounds that are more or less consistent in a statistical sense between training and testing. That's not so good. We can learn biases inherent in the training set and transfer them to the testing set. And that's specifically a within data set phenomenon. If I then would take my trained model and set it out into the world, moving away from the data set, in most cases, as we know, it doesn't work as well. There's this cross data set or real world evaluation effect, and we have a big problem. But you can go even further than that. What I like to term open set recognition. Here you're going to have multiple known classes and many unknown classes. In fact, a near infinite sampling of unknowns coming into the system. And this, in essence, would be like you or I observing scenes in the natural world, making decisions, and processing lots of visual information in real time. So what does the statistical learning literature have to say about this? If you go back to the theoretical work of Vapnik, you often find a formulation that looks somewhat like this. It's termed the fundamental multi-class recognition problem, and it's composed of three pieces. First, we're going to figure out what ideal risk is. How risky is the solution that we have at hand? And we figure this out by integrating over the product of the loss function, which of course is taking outputs from the trained model, which is just f of x here, and checking it against the known ground truth label. And we'll also have our feature vector here that we're submitting into the system. This would probably be a training data point if we're assessing loss. And depending on how far away we are from where we should have been, we assign some penalty. And then, of course, we have a joint distribution here, which would be the co-occurrence of the feature vectors x and the labels y. And to make this work, you would have to know all of this information. You'd have to know all of the classes. But of course, this stuff is undefined for open set recognition because we don't have complete knowledge of the world. So a lot of our notions of risk and supervised learning just get thrown out the door. But is this really a problem in practice? As it turns out, yes. So if we think of something like a linear classifier, we have this situation. Here, I have a binary classifier. It's separating dogs from other things. Here is the decision boundary that was drawn after training. Maybe this is a max margin classifier, so I'm trying to maximize the space between the negative and positives. And this will work to some extent if I'm doing ImageNet or Caltech or whatever computer vision data set I have at hand. But oftentimes, you have this problem where some other object class, which was unknown at training time, pops up in an unexpected place within the broader feature space. Here you can see this raccoon. We didn't have any raccoons when we trained the negative portion of the classifier here. Is showing up on the positive side of the classifier. Why is that happening? If you think about a binary classifier that's simply linear, you have this half space problem. those half spaces extend far out into space. In fact, they have infinite support on either the negative or the positive side of the hyperplane. So what does it mean if you are very far away from the support of your known training data? It means you have a lot of risk in those areas. We don't know what's going to show up very far from the positives or very far from the negatives. Maybe we get positive samples on the negative side or negative samples on the positive side because we always have an impoverished data regime when we're doing machine learning. Even in this grand era of big data, we're not sampling enough information. But we can go to a very simple example to show the drastic impact of this. So take MNIST, which of course we know is this very basic machine learning benchmark, which is widely considered to be solved and has been solved for a very, very long time. But we still use it in machine learning because it's a good baseline. If your algorithm doesn't work on MNIST, you probably have to reconsider a lot of things. But it turns out you can get more mileage out of MNIST if you change up the training protocol. So if we look at the plot on the left here, this is just one versus rest SVM, training on some number of classes and testing on the same number of classes. So closed world, using the data set as it was intended. It's no surprise that SVM is nearly perfect. We know that this data set is basically solved. But now let's do something different. Let's just train on images of digits 0 through 5, and then we're going to test on digits 0 through 9. So we left out some digits, and we brought them back in during testing. And lo and behold, the SVM, giving it a threshold so it can at least attempt to reject data coming into its recognition function, its performance drops dramatically. And in fact, we can take a different algorithm, one that my lab developed that is more tolerant of open set recognition, and it does much better, but it also drops in performance as the world grows to be more open. So this is very curious. We should be doing quite well on MNIST, even for an open set problem, no? Turns out this problem is far more challenging than most people give it credit for. So this is a deep learning workshop, so let me switch now to recontextualize this problem within the space of deep learning. And specifically, we need to think about the readouts that are involved when we make decisions with things like convolutional neural networks. So we all know, I think, the basic story here. I want to do feature learning because I know I can't do something as naive as take the raw pixels because they're corrupted by some noise. And if you look at a two-class problem, say separating images of two individuals, Sam and Joe in this case, this nasty entanglement happens, and this isn't very useful. This is why we have features in computer vision. So we can move then to something like a V1 space, making an analogy to the primate visual system or mammalian visual system in general. These would be features like SIFT and HOG and LBP, the so-called hand-tuned or handcrafted features we were using in computer vision before deep learning became the rage. This gets you somewhat untangled, but we know those features aren't as descriptive as they could be. Again, thinking about the ventral stream in mammalian vision, we know what those features look like. They're essentially Gabor wavelets, these oriented edges that are not tremendously descriptive, but when taken in large ensembles, could be learned over, and it does build useful models. But we can do better than that. And so the story then is deep learning gets us something closer to IT in the brain, which would be well-developed object representations that are separable. And because we have this separation, the classification problem should be trivial. Look, there's a big gap here. I should be able to draw a line right between it. I don't have to do any really sophisticated supervised learning to make a decision. Problem solved. We fixed it at the feature level. So we get some kind of untangled representation. And that's typically what we do when we deal with machine learning for making decisions using deep learning. Here on the left is a bad set of representations because we can't have a clean separation with the hyperplane. But on the right here, this is the ideal situation. My cutting hyperplane went right into that open space between the two classes, and now I can take in any novel inputs for these two individuals, Sam or Joe, and hopefully have no trouble making the distinction. Of course, this doesn't help us with some unknown individual popping up here. We'll extract features with the same network that's used in this model. That's perfectly valid. And of course, our model will give us some decision. We can have some other unknown individual appearing somewhere else in space. Because there's this unknown element, there was no way to account for this when we trained this model. We made this assumption that we wouldn't see anything, but of course, if we're trying to solve real-world vision problems, we have to expect that we're going to see mostly unknown things. So it comes down, as I mentioned before, to this readout layer. What do we stick on the end of a neural network to make a good decision? Pretty much we see this. We just see softmax tacked on the end. We like softmax because it's a logistic function. It gives us a probability value. That's quite useful for interpreting the results out of these networks. But in an open set world, this is problematic because we have to sum over all the classes to compute this function. We don't know what all the classes are, so we can't really use it. Linear SVM, this is also useful. It doesn't inherently give us a probability score, but we could calibrate it. Max margin is useful for making decisions. Maybe we eke out an extra percentage point or two when we're making decisions with our network. Linear SVM, I just showed you, has this half-space problem. In its training regime, it only assumes known positive and negative samples. It's not very good at generalizing when unknowns start to come into the system. What about a distance measure, something like cosine similarity? We see this a lot now in computer vision, especially for large-scale matching problems like video-to-video matching. Distances are good, but we need to estimate some threshold to accept or reject the distance value. Those thresholds are empirically determined. They can only be based on what we know. So this is an image from a paper that appeared last year at CVPR from Jeff Clune's group. Many of you may have seen this. We know that neural networks are prone to fooling images. Using a hill climbing strategy, gradient ascent, you can evolve images that look essentially like nonsense, but just kind of push over the decision boundary and can be classified as some other object. So it may be a little hard to see here on this slide, but all of these are misclassified. In some cases, the misclassifications make no sense at all. There's no visual resemblance between what is shown in the image and what label the classifier assigned it. And so that's a big problem. So is there any solution to this? As it turns out, yes. I'm going to highlight here a paper that's going to appear next week at CVPR by Abhi Bandali at Samsung. And he's arguing that you can have an open set version of the softmax function, something he's calling OpenMax here, which is doing correct probabilistic interpretation of what this input should be and where it should be placed with respect to a decision boundary. So by looking at what Abhi is calling an activation vector for a particular object class, you can kind of figure out where the network is firing. So in these activation patterns here, if you think of this as an x-axis, these are all different classes in ImageNet. Sharks, whales, dogs, fish, baseball are demarcated here. But all the rest of the classes are shown as well. They're just not labeled. And so when you have a particular image, it's going to provoke a response from many similar classes and in some cases dissimilar classes as well. So the idea here with OpenMax is, can you probabilistically calibrate the classification piece, right, OpenMax, so that it's not heavily biasing itself towards the things that are not visually similar, and ideally restricting itself to just the class of interest. And when you do this, the results are actually much better. You solve the fooling image problem. Here, softmax gives 100% confidence in this particular image for being a baseball. With OpenMax, it's getting 0, which is expected. Same thing here for this fooling image meant to be a hammerhead shark. OpenMax rejects it. So what exactly could you do to make this work? What is OpenMax doing that's different from softmax inherently? The idea is you can draw inspiration from the statistical extreme value theory to model decision boundaries. You can think of a lot of these decision-making problems as being problems of extrema. If you think of something like a support vector machine, you have a subsampling of training points that form your decision boundary. Those could be considered to be extrema with respect to the broader class's distribution. There's a special set of statistical tools one uses to create probability models based in that kind of a regime. And that's exactly what this OpenMax function is doing. So once you have good calibration, you can then adjust your weights accordingly and then apply a threshold to reject these unknown inputs. And it makes up for this deficiency. Is it perfect? No, it's a good step in the right direction. But there are further complications I'd like to mention when it comes to open set style evaluation. As it turns out, my lab has found you don't really need to use tricky manipulations to fool convolutional neural networks. You can do things like synthesize objects in many novel configurations, and it's not terribly difficult to get the classifier to make outrageously ridiculous mistakes. So here, we used a computer graphics engine to render different poses of this airliner, and you can see the output of GoogleNet here, hammerhead shark, blow dryer, mosque, I'm not sure how that one was mislabeled, syringe, trimaran, missile, maybe plausible, but certainly no human would assign a label like that to these images. And I'm showing you here 6 images out of millions of images that have all been misclassified. So I want to throw out this question. The organizers of this workshop were kind of prodding us as speakers to come up with provocative questions. So here is mine that I submit to you. Are performance measures actually misleading us when it comes to evaluation, and not just deep learning, but machine learning in general? We've been looking at applying visual psychophysics for evaluation. So this is very different than just looking at mean accuracy, precision recall, area under the curve, all the basic evaluation tools we have in machine learning and computer vision. And when you start to look at patterns of error over varying degrees of difficulty when it comes to the stimuli that you're presenting to the system, it's quite interesting. So here are some results, not even deep learning. This is just face detection, looking at Google's face detector and Facebook's face detector under the presence of occlusion. You can see as the images get to become more difficult, more occluding bars, these detectors fail. In fact, they fail quite quickly. They fail in a place where the humans aren't failing at all, well over here in terms of the x-axis, how much face is present in the image. And the humans, while they drop in performance, even under very heavy occlusion, they never sink down to chance. Humans are very good at face detection. Of course, that makes sense because we're adapted to recognize and detect each other's faces to survive in the wild. So this becomes an interesting way to evaluate deep learning as well. So what my student Brandon has done is create a psychophysics pipeline. We're essentially pretending to be psychologists or neuroscientists trying to understand a black box vision system. But instead of looking at, say, a rodent or a primate, we're looking at models, trained models in the deep learning world. The pipeline first begins by trying to understand what is the class canonical view for a particular network. This would be some canonical representation where the network fires most rapidly, and you get the highest confidence out of, say, your softmax function. Once you've identified your class canonical view, you can manipulate some chosen variable. The whole idea behind psychophysics is that you have very fine-grained control over some variable that you're manipulating to figure out where the perceptual thresholds are of the system at hand. This could be, say, occlusion, which we're showing here. It could be blur. It could be resolution. It could be the pose configuration of the object. Any number of things. You can do this with amazingly fine-grained granularity as well. The canonical example out of the psychology literature is the minimum amount of light that was needed to stimulate a photoreceptor in the retina. That turned out to be a single photon. And that was an experiment that was done, I believe, in the late 1940s. So psychophysics is well established and quite powerful in other realms of science. It's probably important that we bring it in here, too, for machine learning. So once we have hundreds of thousands or millions of manipulated stimuli, we classify those stimuli and get interesting results, which could be misclassifications or correct classifications. And then we could generate what's known as a psychometric curve, which would tell us rather accurately where the perceptual thresholds are for a particular model. And so some examples of something like this. Here's our airliner again. Here we're manipulating the images via Gaussian blur. And you can see that the networks, we have AlexNet, CafeNet, GoogleNet, and 2 variants of VGGNet from the visual geometry group at Oxford, are not doing very well. So how many of you, here's a little quiz, how many of you would mistake this image as something other than a plane? Is anybody not seeing a plane here? No, right? And these networks fail basically over here, somewhere between this image and this image. That's very surprising, considering these are state-of-the-art networks that we're using for all sorts of tasks in computer vision and robotics. The cat, here's another example. Again, how many of you would think that this is something other than a cat? Anybody not seeing a cat here? It's a little bit blurry, but I think we can all see the geometric structure and recognize what this is. Again, these networks are failing long before they get to even this image. And these are not even the most extreme examples. In fact, I cut this plot off in half. We kept going out on the x-axis, but the networks were essentially useless long before we got to the end of the plot. Though we do see varying differences depending on what model we use. Again, it's computer graphics, so sometimes we're at the mercy of the quality of the object model we're using. So here's an example of a chicken. Maybe this one is a bit more difficult. To me, even from here, this looks like a blob, not really like a chicken. So I won't fault the models for failing there. But they failed much sooner here with not that much blur at all. And again, I don't think many people would mistake this chicken for something else. So it's troubling at the very least. How much exhaustive testing has gone into deep learning? Again, I think some of the earlier speakers were poking fun at evaluation in computer vision. Sure, ImageNet is big if you look at the number of instances per class, but there isn't a whole lot of variation within the data set. And there are peculiar biases that were pointed out years ago by Alyosha Ifros and Antonio Torolba in a 2011 CVPR paper on dataset bias. But again, we seem to sort of cheer the superhuman performance of these systems on data sets like that without looking at the psychophysics. So it's something we need to think about. Practical implications, this probably isn't terribly surprising. Autonomous vehicles, self-driving cars have come up a number of times already in this workshop. Here, this is just an article written by my good friend and collaborator, Sam Anthony, discussing the kind of hacking implications something like this could have. One could imagine crafting malicious graffiti, which kind of tickles the decision boundaries of these models in interesting ways, causing cars to veer off the road in unexpected ways. As long as you can do these hill climbing style attacks, this seems possible. If, again, the tolerance isn't there for even very basic image degradations, like small amounts of Gaussian blur, a little bit concerned about how tolerant the cars will be to real-world driving conditions. And so, again, I just wanted to whet your appetite with some of these ideas. I'm happy to take any questions you may have.
Thanks, Walter. Do we have questions?
Yeah.
It was a nice talk. So in your psychophysics experiment, you showed all of these images with like just lines drawn over the.
Oh, the occluding bars, yeah.
Yeah, the occluding bars. Did you look at other types of patterns or noise to add to the images?
Yeah, that's a great question. So we're looking at more naturalistic occlusions because obviously that's fairly contrived. If you look. Surprisingly, this style of testing is used by a number of psychologists, but we feel it's not as realistic as, say, like a face behind some branches or something like that. So what's nice, now that we've moved to a computer graphics engine, we can render all of that on the fly. So we are looking at it. Good question. So my dream with this is once we have a good sense of where the perceptual thresholds are, we can then do reinforcement learning and try to get better at occlusion and blur and all these other things. Again, all of the troubling conditions are kind of baked into the existing data sets but are not identified. It's difficult to say where the model is succeeding or failing right now when we look at ImageNet or COCO or any of these data sets. But here we know exactly. And we can feed that back into the model.
One more question. So can you maybe comment, just thinking if we as roboticists want to make these neural networks work for tasks like object detection, scene understanding in the wild, and seeing these results, what's your feeling? What does that mean? Where are we really with deep learning in robotics? Is it, are we hitting a limit here, a hard limit?
I don't think it's a hard limit. I think we've done poorly as a field in general at contextualizing this work. How good is it? When I first saw deep learning, I was excited because it was a measurable step beyond where we were with SIFT and HOG and LBP and all the hand-tuned descriptors. I didn't think of it as being the solution for AI. But of course, all of the PR followed, the benchmark numbers, and there are some true believers out there that believe, this is the true way to do artificial intelligence. I don't think that's necessarily true. I think we need to be smart about identifying the weaknesses and then address them with more work. I mean, that's just science. So we're not there yet, but we can do better.
Great, thank you, Walter.